Hey, welcome back to part 4 out of 5 for velocity time graphs. You are almost there, you can make it! In this video, we are going to further analyze a velocity time graph. So far, you know that when you grab the slope from a position time graph, you obtain the velocity. If you find the slope on a velocity time graph, you get the acceleration. Now, what happens? What if we want to find the displacement instead, or the change in position from a velocity time graph? What do we do? I'm going to tell you the answer straight up, and I will show you why it is. To find the displacement on a specific time for a specific region of your velocity time graph, you need to find the area underneath the graph. Okay, so what does that look like? What do you mean by the area underneath the graph? So let's say I have a velocity time graph, and then let's say my graph looks like this. I have a positive region, I have a negative region. What the area underneath the graph means is the area between your line and the x-axis. So for this segment, the area underneath the graph would be this part. But when the graph becomes negative, then the area between the line and the x-axis would be this part instead. So that's what that means, is the shading area region between the graph line and the x-axis. That's what it looks like. So the other question you might be wondering is, why area? How does the area work? Does it have any significance? There's a reason, and yes, it totally does. I will show you with this graph that I have down here. Let's say I want to find the area underneath the graph of this particular region here. Okay, so let's shade this in. Now, we know that this area here is a rectangle, okay? So for a rectangle, or for any sort of a shape, usually you have to multiply 2 dimensions. In this case, I'm multiplying the y dimension with the x dimension. So that's here, width times the length in this particular scenario. And it's very similar in the other areas, which we'll see in a moment. So here we have the width here is our velocity measured in meters per second, and we're going to multiply that by the length, which is the time measured in seconds. Okay, so when do we have velocity times time? When have you seen that before? Isn't that similar to when we have to when we did displacement is your velocity. Sorry, remember when we did velocity is your displacement over your time, and then to solve for that, you needed to multiply both sides by your time, so that you get, as a result, you get Vt is equal to d, displacement. If you multiply the 2 dimensions, you get displacement. And that's the same if you look at the units. If you take meters per seconds as your unit and you multiply by the other dimension, which is seconds, your seconds cancel, leaving you with meters. So that's the significance of finding the area underneath a velocity time graph. So let's do some practice. So the practice, I have questions 8 all the way down to F for analyzing a velocity time graph, and then I have another problem down here below for you to try afterwards. Okay, so let's get started. Here we have the question, find the displacement between 0 seconds and 8 seconds, which is exactly there. And the nice thing about that, we already know the area of our rectangles is your width times your length. And in this case, our width is 4 meters per second times a total of 0 to 8. That is a total of 8 seconds, giving us a total of 32 meters going in the positive direction. The next question, we are to find the displacement between 8 seconds and 15 seconds. So that's 8, 9, 10, 11, 12, 13, 14, 15, right there, 15 seconds. So this is a little weird, a bit tricky because the area underneath the graph from here to here at the 9, 10, 11 mark is from the line to the x-axis like that. The second segment is from this line below the x-axis to the x-axis, which is this shaded region. Okay, so we have two triangles here to calculate, and I'm going to break it down into the first part and the second area part. So I'm just going to say our displacement is the sum of the two areas plus area 2, because we're finding the total. And the interesting about area 2 is now is below the graph. We'll talk about that in a second. Now, first things first, what's the equation for the area of a triangle? If you recall, the area of your triangle is your base times height divided by 2. I don't fully expect you to memorize that for a quiz or a test, but I hope it becomes common knowledge enough that you don't need to use to ask for it, that it will become registered in your memory. Anyhow, let's begin. Okay, so first area is a triangle, so that's your base times height divided by 2, plus the second area, same thing. Now in the first area, our base is the time. Okay, the base is 9, 10, 11, so we have 1, 2, 3 seconds total as your base. The height in our first triangle is, and since the squares represent 1, I can just count the squares. 1, 2, 3, 4, and this is positive because we have a positive height, 4 meters per second. All of that divided by 2 for our triangle area. The second segment, we have our base as 1, 2, 3, 4, so that's 4 seconds. And our height, now here's the part you got to be careful. The height is 1, 2, 3, 4, 5, but it's not positive 5, it's negative 5, okay? So we have negative 5 meters per second divided by 2 for the area of a triangle. So this top 3 times 4, 12 divided by 2 is 6 meters plus 4 times negative 5, negative 20. Negative 20 divided by 2 is negative 10. Don't forget the negative, okay? That's very important. So this comes down to a total of negative 4 meters, okay? Now we have the two displacements. We can calculate the total displacement for the entire trip. Now let's add up the two values together. We have 32 meters plus, or in this case minus, we will minus 4 meters, giving us a total of 28 meters. Okay, that's our total displacement. What if we want to find a total distance? Be careful here. Direction does not matter. Meaning we need to make sure we sum up every single bit of distance that this person has traveled. So the first segment, we have a straight up 32 meters going in the positive direction. But the second segment is a little tricky because notice that he goes backwards, and actually he's going forward but slowing down. He still travels the 6 meters, okay, but then he travels 10 meters backwards, and we don't care if it's backwards, we don't care if it's negative, we still need to add those 10 meters. Notice I didn't straight up add the 4 meters because this is just finding the sum out of these two numbers. We have to look at every single motion this person did to find the total distance traveled. That is something we need to be careful of. That gives us a total of 32 plus 10 is 40, 42 plus 6 is 48 meters. Okay, so notice we have a bigger number there. Now we have the displacements and the total distances. We can calculate the average and velocity and the average speed. Our average velocity here, we know that's equal to our total displacement over our total time. Our total displacement is positive 28 meters over the 15 seconds. We calculate that quickly, we get 1.866. 1.866 continuing. We're going to round that off to approximately 2 sig figs, 1.9 meters per second. As for the average speed, this is not our total displacement, but our total distance divided by our total time. And this time we have 48 meters instead over the time of 15 seconds. And we do a quick calculation, we get 3.2 meters per second, direction independent. Okay. All right. So here is the time for you to try this problem that I have here, mirrored very similar to the last question. Okay. Good time to pause, and I will see you back. Okay, now it's my turn. Okay, finding the displacement in the first region looks like a nice square, which is just one side times the other side. Notice it's negative because it's below the x-axis. Then the next segment, we have two parts again because it's broken off by the origin, separating area 1 and area 2. We're talking about triangles, so it's base times height. The first one is 3 seconds for our base and -3 for our height. Second is above the graph, so it's a positive 3 meters per second. We add them up together. Hey, it is 0 because they're symmetrical and same shape. Their total displacement is just the top because the second part is 0. But for distance, we have to add up every single segment, including the separate areas we got in B, giving us a total of 45 meters. Average velocity is just total displacement over total time, and that's just the values that we got above. Over 12 seconds is our total time. Notice it's negative as our average velocity. Now for average speed, it's total distance over total time. We use a total this distance that we calculate above over 12 seconds, giving us positive, well, it's always positive because magnitude, 3.8 meters per second rounded to 2 sig figs. All right, coming back to this problem here. So everything looks pretty much about the same. We have the two areas that we calculated separately here. And the cute thing about this one is notice the area below the graph and above the graph are really symmetric to one another. They're exactly the same shape. So the shapes kind of, if you think about it, they kind of cancel out in a way, giving us 0 meters for question B. That's a cute thing that you might notice when you have two areas above and below the graph that look symmetrical, giving you a total displacement in that region of 0 meters. But then when we calculate the total distance, we have to make sure that we add up these distances separately as positive numbers because we don't care about the direction. The person still walked that far in total. So when we calculate the displacements and the distances for average velocity and speed, these were mirrored, and notice that we got a negative value for average velocity because a person was primarily moving in a negative direction, but for speed we still got a positive value. Okay, so now you know how to find displacement from a velocity time graph. So let's do a quick recap of the little diagram that I drew for us above. Is now you know what the slope means on a position time graph, velocity time graph, and to find the area, to go backwards, you need to find the area underneath the velocity time graph to get the displacement. Actually, I'm going to change that to a D for that purpose. So what do you think for acceleration time graph? What do you think we need to find the, well, actually, it's changing velocity, but that's what we will be talking about in the next video. in the last video. Can you believe it? You made it. You're gonna finish this. It's the last video. Last video, we're gonna talk just about acceleration time graphs and and see if we can put everything together. Okay, good job, guys. And I will see you for part 5. Okay, it's the last video. You can do it. All right, see you back.